So this code is a simple MPI program written in C++ to demonstrate the basics of sending and receiving messages between processes or ranks in a parallel environment. First comes the necessary headers. Sta- I- IOStream is included as it is the standard C++ library for input-output operations. MPI header file is included, which provides MPI function declarations. C-string is included as it is a standard library for string manipulation. Then comes the constant declaration line. In this line, the constant defines the maximum length of the greeting string. Then is the main function. The main function is the entry point of the program. It takes command line arguments, that is an argument vector. Here, MPI initialization is done. MPI underscore init initializes the MPI environment. MPI comp rank gets the rank of the calling process in the communicator. MPI comp size gets the total number of processes in the communicator, that is MPI comp world. Then is the greeting string. This declares a character array to hold the greeting message. Then rank 0 sends the message. When rank is 0, it initializes the greeting string with hello world. Then it sends this greeting to all other processes using MPI send. The length of the greeting string is calculated with std string length plus 1 to include the null terminator. Then other ranks receive the messages. For all the ranks other than 0, they wait to receive a message from rank 0 using MPI receive. The received message is stored in the greeting array. It then prints the received message along with the rank of the process. Then comes MPI finalization. This call finalizes the MPI environment, freeing resources allocated by MPI and ensuring a clean exit. At the end, the main function returns 0 to indicate successful execution. So overall, the program initializes MPI, determines the rank and size of each process. Rank 0 sends a hello world message to all the other ranks. Other ranks receive the message and print it along with their rank. Finally, MPI environment is finalized. This code demonstrates a simple communication pattern in MPI where one process sends the message to multiple processes and receiving processes print the received messages. So this code demonstrates how MPI is broadcasted a message from the master process to all the worker processes. Additionally, it uses POSIX message queues to send and receive messages. So first come the header files that we have included here. The code has several header files. IOStream is included for the input output operations. C string is included for C style string operations. CSTD library is included for standard as it is a standard library for using functions like malloc and exit, cstdio for C-style input-output operations, unistd.h for POSIX operating system API, fcntl.h for file control, sysstart.h for file status and information, mq.h for POSIX message queue functions, mpi.h for MPI functions. Then declaration of constants is done here. Here the queue name is the name of POSIX message queue. Max message size is the maximum size of the message. Then comes the main function. Then comes the initialization. Then comes the declaration of variables for MPI, rank, and size. Then comes the master process. Here, master process with rank 0 broadcasts the message hello world using MPI underscore bcast. This message is of type MPI underscore char and has length of string length message plus 1 to include the null terminator. Then comes the worker process. For the workers processes, ranks that are greater than 0, MPI underscore bcast is used to receive the broadcasted message into receive message. After receiving the message, each worker processes prints the received messages along with its rank. MPI finalizes the MPI to free resources and then returns 0 to indicate the successful execution. So basically, the master processes in this code broadcasts the message hello world to all worker processes using MPI. Worker processes receive the message and print it along with their rank. The code also includes headers and constants related to POSIX messages, queues. So in this code, first of all the necessary header files are included. Then comes the namespaces. These lines declare the namespaces to avoid writing std before every standard library identifier. Std is the namespace for the standard library, and std chrono is the namespace for time related functions. Then the function of random vector is created. This function takes an integer array vector and its size as parameters. It fills the array vector with random integers between 0 and 99. Then comes the main function. Then the line of unsigned long global size comes. Here global size is an unsigned long variable that specifies the size of the arrays to be generated. It sets to 100 million. Then comes the sRandom function. This initializes the random number generator at the current time. This ensures that each time the program runs, it generates different random numbers. Here, three integer pointers v1, v2, and v3 are declared and memory is allocated to them dynamically using malloc. Each array is allocated memory to store global size number of integers. The random vector function is called twice to fill v1 and v2 with random integers. Auto start high resolution check clock now means start here captures the current time before the addition operation. Then comes the for loop. This loop performs moment-wise addition for the arrays v1 and v2 and stores the result in v3. Then comes the auto stop. The stop captures the current time after the addition operation. Auto duration cast microsecond calculates the duration between start and stop in microseconds and stores it in the duration variable. Then comes the cout. So here, finally, the time taken for the addition operation is printed in microseconds. The dynamically allocated memory is stored to memory for V1, V2, and V3 is free to avoid memory leaks, and the main function returns 0, indicating the successful execution of the program. Overall, the program generates two random integers array v1 and v2 of size 100 million, performs element-wise addition of these arrays, and measures the time taken for the addition operation. The result printed to the console in microsecond. Finally, the dynamically allocated memory is freed to prevent the memory leaks. So this code performs a simple vector addition using OpenMP to parallelize the computation. First comes the header files. Chrono for measuring the time duration. IOStream for input and output operations. CSTD library provides functions for memory allocation, random number generation, etc. CTime for getting the current time, and OMP.h OpenMP header for parallel programming. Then I have declared the namespace declarations here. std is the standard namespace for C++, and std chrono is the namespace for time related functionalities. Then comes the function of random vector. This function generates random numbers between 0 and 99 and assigns them to the elements of the given array vector of the size. Then is the main function. Then comes the line unsigned long global size. Here, the global size declares the total number of elements in the vector. Then, declaration of s random time is done. It seeds the random number generator using the current time. Here, the memory allocation of v1, v2, and v3 of size global size is done. A random vector v1 and v2. It populates v1 and v2 with random numbers using random vector function. Then comes the auto start high resolution clock. It records the current time before the parallel computation starts. Here, the parallel computation using OpenMP is done. Each thread will compute a subset of the vector addition. Auto stop, high resolution clock, records the current time after the parallel computation ends. Auto duration cast microseconds, calculates the duration of the parallel computation in microseconds. C out, time taken by the multi-threaded function, gives the output of the time taken by the parallel computation. Here, the dynamically allocated memory gets free from the vectors and returns 0 to indicate successful execution of the program. So basically, the program creates larger integer arrays v1 and v2, fills them with the random numbers, and then calculates their sum element wise into v3 using OpenMP for parallel execution. Finally, it measures the time taken for this operation and outputs it.